Hello there, and welcome to the Sleepy Science Channel. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring the universe itself. Not just one galaxy or star, but the vast expanding whole. We'll move gently from fact to fact, learning about black holes, ancient light, distant galaxies, and the gentle dance of cosmic forces. Some things may surprise you. Others may stay with you like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. The universe is mostly empty space. When you look up at the night sky filled with stars, it's easy to think the universe is crowded. But in reality, most of the universe is empty. The distances between stars are so vast that if you were traveling at the speed of light, it would take years to reach even the nearest one. Galaxies are separated by millions of light years of near-perfect vacuum. Even within atoms, the space between the nucleus and electrons is proportionally enormous. If an atom were the size of a football stadium, the nucleus would be a marble at the center. Everything you see, all the matter in the universe, occupies only a tiny fraction of space. The rest is silence, emptiness, and dark. There are more stars in the universe than grains of sand on all of Earth's beaches. Astronomers estimate there are between 100 and 400 billion stars in the Milky Way galaxy alone, and there are roughly 2 trillion galaxies in the observable universe. That means there are approximately 200 billion trillion stars out there. Meanwhile, scientists estimate there are about 7.5 quintillion grains of sand on all the beaches and deserts on Earth. The stars outnumber them by a factor of thousands. Each of those stars is a sun, many with their own planets, moons, and perhaps even life. The universe is not just big, it's incomprehensibly vast. Light from distant stars has been traveling for billions of years. When you look at the night sky, you're not seeing the stars as they are now. You're seeing them as they were when their light began its journey. The North Star's light takes about 430 years to reach Earth. Some stars you see are hundreds or thousands of light years away. And when we look at distant galaxies with telescopes, we're seeing them as they were billions of years ago, not long after the universe began. In a very real sense, looking into space is looking back in time. The deeper we look, the further back we see. The universe shows us its history, one photon at a time. The universe is expanding, and it's getting faster. And in 1929, Edwin Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they're moving. This means the universe itself is expanding. Space is stretching, carrying galaxies apart. But in the late 1990s, astronomers discovered something even stranger. The expansion is accelerating. Some mysterious force, which we call dark energy, is pushing the universe apart faster and faster. We don't know what dark energy is, but it makes up about 68% of the universe. The cosmos is not just growing. It's growing faster, driven by something we can't see or fully understand. Black holes are places where gravity is so strong that nothing can escape. When a massive star runs out of fuel and collapses, it can form a black hole. a region where gravity is so intense that not even light can get out. The boundary around a black hole is called the event horizon. Once you cross it, there's no going back. Everything that falls in is pulled toward the center, the singularity, a point of infinite density. We can't see black holes directly, but we can observe their effects. They bend light, heat up surrounding gas, and warp the fabric of space and time itself. Black holes are the universe's deepest wells, silent and invisible, waiting in the dark. There are galaxies moving away from us faster than the speed of light. This sounds impossible, but it's true. Einstein's theory of relativity says nothing can move through space faster than light. But space itself can expand faster than light. In fact, the most distant galaxies are receding from us at speeds greater than light speed because of the expansion of space. This means we'll never be able to reach them, even if we could travel at light speed. Their light will never catch up to us. They're beyond a cosmic horizon, forever out of reach. The universe is pulling itself apart, and some of it is already gone from view. Stars are born in clouds of gas and dust. In the cold, dark regions of space, enormous clouds of hydrogen and helium drift quietly. These molecular clouds can be hundreds of light years across. Under the influence of gravity, parts of the cloud collapse inward, growing denser and hotter. Eventually, the core becomes so hot and dense that nuclear fusion begins. Hydrogen atoms fuse into helium, releasing vast amounts of energy. A star is born. This process is happening right now in places like the Orion Nebula, where thousands of new stars are forming. Stars don't appear suddenly. They grow slowly over millions of years from the quiet gathering of gas in the dark. The sun is just one of billions of ordinary stars. Our sun seems special to us. It lights our days, warms our planet, and makes life possible. But in the grand scale of the universe, it's utterly ordinary. It's a medium-sized, middle-aged star, one of hundreds of billions in the Milky Way alone. There are stars much larger, much hotter, and much brighter. There are also stars smaller, cooler, and dimmer. The sun is not unique. It's just one star among countless others, quietly burning in an outer arm of a spiral galaxy, in a universe filled with galaxies. And yet, to us, it's everything. Neutron stars are so dense that a teaspoon of their material would weigh 1 billion tons. When a massive star explodes in a supernova, it can leave behind a neutron star, the collapsed core of incredible density. Neutron stars are only about 12 miles across, but they contain more mass than the sun. The matter inside is packed so tightly that protons and electrons merge into neutrons. A single teaspoon of neutron star material would weigh as much as Mount Everest or more. These stars also spin incredibly fast, sometimes hundreds of times per second, and have magnetic fields trillions of times stronger than Earth's. They're the densest objects in the universe, aside from black holes, compressing the mass of a star into a city-sized sphere. The Milky Way and Andromeda galaxies are on a collision course. In about 4 billion years, the Milky Way will collide with the Andromeda galaxy, our nearest large galactic neighbor. Don't worry, though. The collision will be more of a merger than a crash. Stars are so far apart that very few, if any, will actually collide. Instead, the two galaxies will pass through each other, their gravity pulling them back together again and again, until they eventually merge into a single, larger galaxy. The night sky will look very different during this time, filled with new stars and glowing gas clouds. But by then, the sun will be nearing the end of its life, and Earth will be a very different place, if it still exists at all. Time moves slower near massive objects. According to Einstein's theory of general relativity, gravity warps space and time. The stronger the gravity, the slower time flows. Near a black hole, where gravity is extreme, time slows dramatically compared to regions far away. If you could watch someone fall toward a black hole, you'd see them slow down, freeze, and eventually fade away as their light becomes too redshifted to see. To them, time would seem normal, but to you, watching from a distance, they'd appear to take forever to reach the event horizon. Time is not absolute. It bends, stretches, and slows in the presence of mass and energy. The cosmic microwave background is the oldest light in the universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, and light was able to travel freely for the first time. That ancient light has been traveling ever since, stretched by the expansion of the universe into microwaves. We can detect this light today as a faint glow coming from all directions. It's called the cosmic microwave background, and it's the oldest thing we can observe directly. It's the afterglow of the Big Bang, a snapshot of the universe in its infancy, still visible after more than 13 billion years. This light has been traveling longer than stars have existed, carrying the memory of the universe's birth. There are planets made of diamond. In some star systems, the chemistry is very different from our own. If a planet forms with more carbon than oxygen, and the conditions are right, that carbon can crystallize under pressure. Astronomers have found evidence of such planets orbiting pulsars, dense remnants of dead stars. These planets may be composed largely of diamond, giant crystalline worlds glittering in the dark. They wouldn't look like jewels up close, too hot, too dim, but beneath their surfaces, vast structures of pure carbon could stretch for thousands of miles. The universe is full of strange worlds, places where the familiar rules of chemistry create alien landscapes we're only beginning to imagine. The universe has no center. It's natural to think the Big Bang happened at a specific point and everything expanded outward from there. But that's not quite right. The Big Bang happened everywhere at once. Space itself expanded, carrying matter with it. There's no central point from which everything is moving away. Every point in the universe can claim to be the center, because from every point, all other galaxies appear to be moving away. It's like dots on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot, but there's no center on the surface. The universe is the same, but in 3 dimensions. Everywhere is the center. Nowhere is the center. Some stars are older than the universe seems to allow. Astronomers have found stars that appear to be older than the universe itself, which is about 13.8 billion years old. These stars, called population 2 stars, are metal poor, meaning they formed very early. Their ages are estimated by their composition and brightness, and some calculations put them at over 14 billion years old. This creates a paradox. How can something be older than the universe? The answer is likely that our measurements have some uncertainty. The stars are probably just slightly younger, or the universe slightly older than we think. But the discrepancy is a reminder that our understanding is still incomplete. The universe holds puzzles we're still trying to solve. Rogue planets drift through space without a sun. not all planets orbit stars. Some have been ejected from their solar systems by gravitational interactions, flung out into interstellar space. Others may have formed on their own, like failed stars. These rogue planets wander the galaxy in darkness, cold and alone, with no sun to warm them. Astronomers estimate there could be billions of them in the Milky Way, possibly even more than there are stars. They're nearly impossible to detect unless they pass in front of a star or glow faintly in infrared. Each one is a silent world, drifting through the void, a planet without a day, spinning in endless night. Gravity is the weakest of the fundamental forces. There are 4 fundamental forces in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Of these, gravity is by far the weakest. A tiny fridge magnet can overcome the gravitational pull of the entire Earth when it picks up a paperclip. But gravity has 2 important properties. It acts over infinite distances, and it's always attractive. Every object with mass pulls on every other object with mass. Over cosmic scales, gravity dominates, holding planets in orbit, binding galaxies together, and shaping the structure of the universe. It's weak, but patient and relentless, a gentle hand that guides the cosmos. The sun converts 4 million tons of mass into energy every second. In the core of the sun, hydrogen atoms fuse together to form helium, releasing energy in the process. According to Einstein's famous equation, E equals mc squared. Mass can be converted into energy. The sun does this constantly, turning about 4 million tons of matter into pure energy every second. This energy radiates outward, eventually reaching Earth as sunlight. The sun has been doing this for about 4.6 billion years, and will continue for another 5 billion or so. Despite losing all that mass, the sun is so enormous that it's barely affected. It's a slow, steady burning that will last longer than most stars. There are more planets than stars in the Milky Way. For most of history, we didn't know if other stars had planets. Now, thanks to telescopes like Kepler, we've discovered thousands of exoplanets. Based on these findings, astronomers estimate that nearly every star has at least one planet, and many have multiple. That means there are hundreds of billions of planets in our galaxy alone. Some are rocky like Earth. Others are gas giants like Jupiter. Some orbit close to their stars, scorched and barren. Others are far away, frozen and dark. Each planet is a world, with its own geology, atmosphere, and history. The galaxy is full of worlds, most of which we'll never see. The observable universe has a boundary, but it's not an edge. The observable universe is the part of the universe we can see, limited by the speed of light and the age of the universe. Light from beyond this boundary hasn't had time to reach us yet. This boundary is about 46 billion light-years away in all directions, making the observable universe about 93 billion light-years across. But this isn't an edge. There's no wall or border. The universe almost certainly continues beyond what we can see, possibly infinitely. We're just limited by how far light has traveled since the Big Bang. Beyond our horizon, there's more universe, more galaxies, more stars forever out of reach. Space is not completely empty. Even the darkest, most remote regions of space contain something. There are stray atoms of hydrogen, a few particles per cubic meter. There's also the cosmic microwave background radiation, the faint glow left over from the Big Bang. Quantum physics tells us that even a perfect vacuum isn't truly empty. Virtual particles pop in and out of existence constantly. a quantum foam underlying all of reality. Magnetic fields, gravitational waves, and dark matter also permeate space. The vacuum is active, humming with subtle energy. Space is not nothing. It's a field, a medium, a stage on which the universe performs. Stars twinkle because of Earth's atmosphere, not because they flicker. When you look at a star, it appears to twinkle, but the star itself is shining steadily. The twinkling is caused by turbulence in Earth's atmosphere. As light from the star passes through layers of air with different temperatures and densities, it bends slightly, making the star's position and brightness seem to shift rapidly. This is why astronomers prefer space telescopes. Above the atmosphere, stars shine with a steady, unwavering light. Planets, which are much closer, appear as small disks rather than points of light, so they don't twinkle as much. The twinkling is not a property of the stars. It's a property of the air between us and them. The universe could end in a big freeze, big rip, or big crunch. Cosmologists have several theories about the ultimate fate of the universe. In the big freeze, the universe continues expanding forever, growing colder and darker as stars burn out and galaxies drift apart, until everything reaches a state of maximum entropy. In the Big Rip, dark energy becomes so strong that it tears apart galaxies, stars, planets, and eventually atoms themselves. In the Big Crunch, gravity eventually overcomes expansion, and the universe collapses back into a singularity. We don't know which, if any, will happen. The end is trillions of years away. For now, the universe is young, vibrant, and full of light. Galaxies come in different shapes. Some galaxies are spirals like the Milky Way, with arms of stars, gas, and dust swirling around a central bulge. Others are elliptical, smooth and featureless, containing mostly old stars. There are also irregular galaxies, which have no clear structure, often the result of gravitational interactions or collisions. Galaxies can be small, with just a few million stars, or enormous, with trillions. They can be bright and active, with supermassive black holes at their centers, or quiet and dim. Each galaxy is a community of stars, a vast island in space, held together by gravity, evolving over billions of years. The speed of light is the universe's speed limit. Nothing can travel faster than light in a vacuum, about 186,000 miles per second. This isn't just a rule. It's woven into the fabric of space and time. As you approach the speed of light, time slows down, and your mass increases, making it harder and harder to accelerate. At the speed of light, time would stop, and your mass would be infinite. Only massless particles, like photons, can travel at this speed. This limit means that the universe is vast and unreachable. Even traveling at light speed, it would take over 4 years to reach the nearest star. The universe imposes a speed limit, and it keeps us local. Supernovae can briefly outshine entire galaxies. When a massive star runs out of fuel, its core collapses, and the outer layers explode in a supernova, one of the most energetic events in the universe. For a few weeks, a single supernova can shine as brightly as billions of stars, outshining its entire host galaxy. The explosion scatters heavy elements like carbon, oxygen, and iron into space, seeding future generations of stars and planets. Supernovae are both destructive and creative, ending one star's life while enriching the cosmos with the building blocks of new worlds. They're the forges of the elements, the alchemists of the universe. Dark matter makes up most of the matter in the universe. When astronomers measure the mass of galaxies, they find something strange. The visible matter, stars, gas, and dust, isn't enough to explain the galaxy's rotation speeds and gravitational effects. There must be more mass, something invisible. We call it dark matter, and it makes up about 27% of the universe, compared to just 5% for normal matter. We don't know what dark matter is. It doesn't emit, absorb, or reflect light. We only detect it through its gravitational influence. It's a mystery, a shadow that shapes galaxies, a presence we can't see but know is there. The universe is about 13.8 billion years old. By measuring the cosmic microwave background and the expansion rate of the universe, scientists have determined that the Big Bang happened approximately 13.8 billion years ago. That's the age of the universe, the time since space, time, and matter came into existence. In that time, the universe has expanded from a hot, dense state to the vast, cool cosmos we see today. Stars have formed and died, galaxies have merged, and on at least one small planet orbiting an ordinary star, life emerged and began to look back, to wonder, to measure the age of everything. The universe is old, but not infinitely so. It had a beginning. You can see another galaxy with your naked eye. On a clear, dark night, you can see the Andromeda galaxy without a telescope. It appears as a faint, fuzzy patch of light in the constellation Andromeda. It's about 2.5 million light-years away, meaning the light you're seeing left Andromeda long before humans existed. Andromeda is a spiral galaxy like the Milky Way, containing about 1 trillion stars. Seeing it with your own eyes is humbling. You're looking at an entire galaxy, a vast island of stars, billions of years old, slowly moving toward us. It's the farthest thing you can see without any equipment, a distant neighbor in the cosmic night. Most of the universe is made of things we don't understand. About 95% of the universe is dark matter and dark energy, neither of which we can directly observe. We know they exist because of their effects. Dark matter through gravity, dark energy through the accelerating expansion of the universe, but we don't know what they're made of. The remaining 5% is ordinary matter, the stuff of stars, planets, and people. Everything we've ever seen, touched, or studied is just a tiny fraction of what's out there. The universe is mostly mystery, mostly unknown. We're like children staring into the dark, trying to understand what we cannot see. The sun's light takes about 8 minutes to reach Earth. When you look at the sun, you're seeing it as it was 8 minutes ago. That's how long it takes for light to travel the 93 million miles from the sun to Earth. If the sun suddenly disappeared, we wouldn't know for 8 minutes. We'd still see it shining, still feel its warmth until the last light arrived. The same is true for everything in space. The moon's light is delayed by about 1.3 seconds. Light from Jupiter takes about 40 minutes. When we look at the universe, we're always looking into the past. The present is always just out of reach. Pulsars are spinning neutron stars. Some neutron stars spin incredibly fast, hundreds of times per second, and emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse. If the beam points toward Earth, we see regular pulses of light, radio waves, or X-rays. These objects are called pulsars. They're extraordinarily precise, some keeping time more accurately than atomic clocks. pulsars were first discovered in 1967, and at first, astronomers thought they might be signals from alien civilizations because of their regularity. But they're natural, the lighthouses of the cosmos, spinning in the dark, marking time with perfect rhythm. Space smells like seared steak and burnt metal. Astronauts who have gone on spacewalks report that space has a distinct smell. They don't smell it while they're outside, since they're in spacesuits. But when they come back in and remove their helmets, the smell clings to their suits and equipment. The odor is often described as metallic, like burnt steak or welding fumes. It's caused by high-energy particles, cosmic rays, and the byproducts of reactions on the surface of the suit. Space doesn't really have a smell, since there's no air, but the things that come back from space carry traces of the void, a sharp, unfamiliar scent from beyond the atmosphere. There's a giant cloud of alcohol in space. In a region of space called Sagittarius B2, near the center of the Milky Way, there's a vast cloud of gas that contains ethyl alcohol, the same type found in alcoholic drinks. The cloud is enormous, about 1,000 times the diameter of our solar system. It also contains other organic molecules, suggesting that the building blocks of life are common in the universe. Of course, the alcohol is mixed with other gases and is far too diffuse to drink. But it's a reminder that space is full of chemistry, molecules forming and reacting in the cold dark, creating complex compounds that might one day lead to life. Stars don't actually twinkle when viewed from space. From Earth, stars twinkle because their light passes through the atmosphere, which bends and distorts it. But in space, above the atmosphere, stars shine with a steady, constant light. Astronauts and space telescopes see stars as unwavering points of light, perfectly still. This is one reason why space-based telescopes like Hubble can take such clear images. Without the blurring effect of the atmosphere, they can see finer details. The stars themselves are steady. It's our atmosphere that makes them dance. The Milky Way is on a collision course with other galaxies too. Andromeda gets most of the attention, but the Milky Way is also interacting with smaller galaxies. The large and small Magellanic Clouds are satellite galaxies orbiting the Milky Way. Over time, they'll likely merge with us. There are also streams of stars from other small galaxies that the Milky Way has already consumed, remnants of past collisions. Galactic cannibalism is common. Large galaxies grow by absorbing smaller ones. It's a slow, gentle process, taking hundreds of millions of years, but it's happening now, and it will continue. The Milky Way is still eating. The hottest place in the universe is inside a particle accelerator. The hottest natural temperatures are found in the cores of massive stars and in the moments after the Big Bang. But humans have created even hotter conditions in particle accelerators like the Large Hadron Collider. By smashing particles together at near light speed, scientists have created temperatures over 5 trillion degrees Celsius, hotter than the core of the sun, hotter than a supernova, hotter than anything that exists naturally today. These extreme temperatures last only a fraction of a second, but they allow us to recreate conditions from the early universe and study the fundamental laws of physics. In a way, we're bringing the Big Bang back to life, one collision at a time. A day on Venus is longer than a year on Venus. Venus rotates on its axis very slowly, taking about 243 Earth days to complete one rotation. But it orbits the Sun faster, taking about 225 Earth days to complete one orbit. This means a day on Venus, sunrise to sunrise, is longer than a Venusian year. Venus also rotates backward compared to most planets, meaning the sun rises in the west and sets in the east. It's a strange, slow world with thick clouds, crushing atmospheric pressure, and surface temperatures hot enough to melt lead. Venus is Earth's neighbor, but it's utterly hostile. A reminder that not all worlds are welcoming. There's a giant storm on Jupiter that's been raging for centuries. The Great Red Spot is a massive storm in Jupiter's atmosphere, a swirling oval of clouds about twice the size of Earth. It's been observed for at least 350 years, possibly longer, making it one of the longest-lasting storms in the solar system. Wind speeds inside the storm can exceed 400 miles per hour. The storm is slowly shrinking, though, and scientists aren't sure why. It may eventually disappear, or it may stabilize. Jupiter's atmosphere is turbulent and dynamic, with storms and bands of clouds constantly shifting. The Great Red Spot is the most famous feature, a centuries-old tempest on a giant world. Saturn's rings are made of ice and rock. The rings of Saturn are one of the most beautiful sights in the solar system. They're made of countless particles, ranging in size from tiny grains to house-sized boulders, all orbiting the planet. Most of the material is water ice, mixed with rock and dust. The rings are surprisingly thin, only about 30 feet thick in most places, but they stretch out for hundreds of thousands of miles. They may have formed from a moon that got too close and was torn apart by gravity, or from leftover material from Saturn's formation. The rings are temporary, slowly spiraling into the planet. In a few 100 million years, they may be gone. Europa, a moon of Jupiter, might have an ocean beneath its ice. Europa is covered in a thick layer of ice, but underneath, there may be a vast ocean of liquid water. The moon is heated by tidal forces from Jupiter's gravity, which could keep the water from freezing. If there's liquid water, there might also be life. Simple organisms living in the dark, feeding on chemicals from the ocean floor. Europa is one of the best places in the solar system to search for extraterrestrial life. Future missions may drill through the ice to explore the ocean below. It's a frozen world with a hidden sea, a place of mystery and possibility. The asteroid belt is mostly empty space. When you picture the asteroid belt between Mars and Jupiter, you might imagine a dense field of tumbling rocks. But in reality, the asteroids are spread out over an enormous volume of space. The average distance between them is hundreds of thousands of miles. Spacecraft pass through the belt regularly without any risk of collision. There are millions of asteroids, but they're so far apart that the belt is mostly empty. The total mass of all the asteroids combined is less than the mass of Earth's moon. It's not a crowded highway. It's a sparse scattering of rocky remnants from the early solar system. Mars once had rivers, lakes, and possibly oceans. The surface of Mars is covered with ancient riverbeds, delta formations, and mineral deposits that only form in the presence of water. Billions of years ago, Mars had a thicker atmosphere and liquid water on its surface. It may have been a warm, wet world, possibly even hospitable to life. But over time, Mars lost its magnetic field, and the solar wind stripped away its atmosphere. The water evaporated or froze beneath the surface. Today, Mars is cold and dry, a desert planet with a thin atmosphere. But its past was different, and beneath the surface, there may still be pockets of water, perhaps even life. Titan, a moon of Saturn, has lakes of liquid methane. Titan is the only moon in the solar system with a thick atmosphere, and it's the only place besides Earth where stable bodies of liquid exist on the surface. But instead of water, Titan's lakes and seas are made of liquid methane and ethane. The moon is cold, about minus 290 degrees Fahrenheit, which allows methane to exist as a liquid. Titan has weather with clouds, rain, and rivers, all made of hydrocarbons. It's an alien world with familiar processes, a place where the rain is flammable and the rocks are made of ice. Titan is one of the most intriguing moons, a place that feels both strange and strangely familiar. The moon is slowly drifting away from Earth. Every year, the moon moves about 1.5 inches farther from Earth. This happens because of tidal forces. The moon's gravity creates tides on Earth, and the friction from those tides transfers energy, gradually pushing the moon into a higher orbit. Billions of years ago, the moon was much closer, and the days were shorter. In the far future, the moon will be farther away, and the days will be longer. Eventually, Earth and the moon may become tidally locked, always showing the same face to each other, but that's billions of years away. For now, the moon drifts slowly and steadily, 1 inch at a time. Pluto has a heart-shaped glacier. When the New Horizons spacecraft flew by Pluto in 2015, it revealed a world more complex and beautiful than anyone expected. One of the most striking features is a large, heart-shaped region of smooth ice called Sputnik Planitia. It's made of frozen nitrogen, carbon monoxide, and methane. The ice flows slowly, like a glacier, renewing the surface and erasing craters. Pluto also has mountains made of water ice, as hard as rock in the extreme cold, and a thin atmosphere that freezes and falls as snow when Pluto is farthest from the sun. It's a small, distant world, but it's geologically active and surprisingly dynamic, a tiny heart beating at the edge of the solar system. The sun will eventually become a red giant. In about 5 billion years, the sun will run out of hydrogen in its core. It will begin fusing helium instead, and as it does, it will expand, becoming a red giant. The sun will grow so large that it will likely engulf Mercury and Venus, and possibly even Earth. The outer layers of the sun will be shed, forming a glowing shell of gas called a planetary nebula. What's left of the core will shrink into a white dwarf, a dense, cooling ember about the size of Earth. The sun will no longer shine. It will simply fade over billions of years, a quiet ending to a life that lasted 10 billion years. There are galaxies we will never be able to reach, because the universe is expanding, and the expansion is accelerating. Some galaxies are moving away from us faster than the speed of light. This doesn't violate relativity. It's space itself that's expanding, not the galaxies moving through space. But it means that no matter how fast we travel, we'll never reach those galaxies. The light from them will continue to arrive for a while, but eventually, even that will be redshifted into invisibility. These galaxies are beyond the cosmic horizon, forever out of reach. The universe is pulling itself apart, and some of it is already lost to us. The universe might be infinite. We don't know if the universe has an edge or if it goes on forever. The observable universe has a boundary, about 46 billion light-years away, but that's just the limit of what we can see. Beyond that, the universe likely continues. It might be infinite in size, stretching on forever in all directions, Or it might be finite but unbounded, like the surface of a sphere. You could travel in a straight line forever and never reach an edge, eventually returning to where you started. We may never know. The universe might be too large for us to ever measure, a mystery that will remain unsolved. Galaxies are moving away from us, but the stars in the night sky are not. The expansion of the universe is causing distant galaxies to move away, but the stars you see at night are part of the Milky Way. They're bound to our galaxy by gravity, so they're not moving away due to cosmic expansion. In fact, some stars are moving toward us, and others away, depending on their individual motions through the galaxy. The expansion of space only affects objects that are not gravitationally bound. On smaller scales, like within galaxies or clusters of galaxies, gravity dominates, and expansion has no effect. The universe expands, but locally, things stay together. The Big Bang wasn't an explosion in space. It's easy to imagine the Big Bang as a bomb going off in empty space, but that's not what happened. The Big Bang was the beginning of space itself. Before it, there was no space, no time, no matter. The universe didn't expand into anything. Space itself expanded, carrying matter and energy with it. There was no center, no edge. Every point in space was part of the Big Bang. It happened everywhere at once. The universe didn't explode outward from a point. It grew from everywhere, all at once, creating space and time as it went. Some stars are cool enough to touch. Most stars are incredibly hot. The surface of the sun is about 10,000 degrees Fahrenheit. But there are stars called brown dwarfs that are much cooler. The coolest known brown dwarf has a surface temperature of about 80 degrees Fahrenheit, cooler than a hot summer day. At that temperature, you could theoretically touch it, though you'd still be crushed by its gravity and poisoned by its atmosphere. Brown dwarfs are sometimes called failed stars because they're not massive enough to sustain hydrogen fusion. They glow faintly from leftover heat and slowly cool over billions of years. They're more like giant planets than stars, but they're too big to be planets. They're in-between objects, strange and dim. The universe has no up or down. In space, there's no absolute direction. What we call up and down on Earth is just relative to the planet's gravity. But in the vastness of space, there's no universal orientation. Galaxies are tilted at all angles. Some stars orbit clockwise, others counterclockwise. There's no top or bottom to the universe, no universal north or south. Every direction is equally valid. When astronauts float in the International Space Station, they can orient themselves any way they like. There's no falling, because there's no down. It's disorienting at first, but it's the natural state of things. In the cosmos, direction is relative, personal, and ever-changing. White dwarfs will eventually become black dwarfs. After a star like the Sun becomes a white dwarf, it slowly cools over billions of years. Eventually, it will stop glowing altogether, becoming a black dwarf, a cold, dark cinder floating through space. But the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still faintly glowing. It will take trillions of years for them to cool completely. Black dwarfs are theoretical, objects that will exist in the far future when the universe is old and cold. They'll be the final resting state of most stars, silent and invisible, drifting through the dark. Space is completely silent. Sound is a vibration that travels through a medium like air or water. In the vacuum of space, there's no air, so there's no sound. Explosions, collisions, and engines all happen in complete silence. This is why, in realistic depictions of space, there's no noise. The roar of a rocket engine, the blast of a supernova, the collision of galaxies, all of it happens without a sound. Astronauts can communicate by radio, where sound is converted to electromagnetic waves, but outside their suits, space is perfectly quiet. It's a silence deeper than any on Earth, a stillness that has never been broken. The universe is flat. When cosmologists say the universe is flat, they don't mean it's like a sheet of paper. They mean its geometry is Euclidean, that parallel lines stay parallel, and the angles of a triangle add up to 180 degrees. This is determined by measuring the cosmic microwave background and the distribution of galaxies. If the universe had too much mass, it would curve back on itself like a sphere. Too little, and it would curve outward like a saddle. But measurements show it's right in between, flat or very close to it. This has implications for the size and fate of the universe, but it doesn't change what we see. Flat or curved, the universe looks the same from here. Some moons are geologically active. We usually think of moons as dead, lifeless rocks, but some are surprisingly active. Io, a moon of Jupiter, is the most volcanically active body in the solar system, with lava lakes and eruptions constantly reshaping its surface. Enceladus, a moon of Saturn, shoots geysers of water ice into space from an underground ocean. Triton, a moon of Neptune, has geysers of nitrogen. These moons are heated by tidal forces, the gravitational pull of their parent planets flexing and heating their interiors. They're small worlds, but they're alive with motion, heat, and change. Surprising reminders that geology happens far beyond Earth. The moon has moonquakes. Just as Earth has earthquakes, the moon has moonquakes. They're caused by tidal stresses from Earth's gravity, temperature changes, and impacts from meteorites. Moonquakes can last much longer than earthquakes because the moon's interior is dry and rigid, allowing seismic waves to travel farther and longer. Astronauts left seismometers on the moon during the Apollo missions, and they recorded thousands of moonquakes over several years. The moon is not geologically dead. It still shifts, cracks, and rumbles, a quiet reminder that even airless worlds are not perfectly still. Mercury has ice at its poles. It seems strange, but the closest planet to the Sun has water ice. Mercury's poles have deep craters that never see sunlight, and in these permanently shadowed regions, temperatures drop low enough for ice to exist. Radar observations have confirmed the presence of ice, likely deposited by comets or formed from hydrogen and oxygen in the planet's thin atmosphere. The rest of Mercury is scorching hot, with surface temperatures reaching 800 degrees Fahrenheit. But in the shadows, it's cold enough to preserve ice. It's a world of extremes, where fire and ice coexist on the same small planet. There are stars that orbit black holes incredibly fast. Near the supermassive black hole at the center of the Milky Way, there are stars that orbit at tremendous speeds. One star, called S2, completes an orbit in just 16 years, reaching speeds of about 3% the speed of light at its closest approach. These stars allow astronomers to test Einstein's theory of general relativity in an extreme environment. They've confirmed that time slows near the black hole, and that space itself is warped. Watching these stars is like watching a cosmic clock, measuring the curvature of space and the pull of an invisible giant. Comets are dirty snowballs. Comets are made of ice, dust, and rock, leftovers from the formation of the solar system. They spend most of their time in the outer solar system, cold and inactive. But when their orbits bring them close to the sun, the ice begins to vaporize, creating a glowing coma and a tail that can stretch for millions of miles. The tail always points away from the sun, pushed by the solar wind. Comets have been feared and revered throughout history, seen as omens or messengers. But they're just ancient ice, melting slowly in the sunlight, brief and beautiful visitors from the deep cold. The Oort cloud is a shell of icy objects surrounding the solar system. Far beyond the orbit of Neptune, perhaps a light year away, there's a vast, spherical cloud of icy bodies. This is the Oort cloud, a reservoir of comets that marks the edge of the sun's gravitational influence. It contains trillions of objects, most smaller than a mountain, but some much larger. Occasionally, gravitational disturbances send one of these objects falling toward the inner solar system, where it becomes a comet. The Oort cloud has never been directly observed. It's too far and too dim, but its existence is inferred from the orbits of long-period comets. It's the solar system's outermost boundary, a halo of frozen remnants. There are planets that orbit two stars. In some star systems, two stars orbit each other, and planets orbit both of them. These are called circumbinary planets. Standing on such a planet, you'd see two suns in the sky, rising and setting together or at different times. The most famous example is Kepler 16b, a gas giant about the size of Saturn. These planets are surprisingly common, and their orbits can be stable despite the complex gravitational dynamics. They're real-world Tatooine, worlds lit by twin suns, where the sky holds twice the light and shadows fall in strange directions. Venus rotates backward. Most planets in the solar system rotate in the same direction they orbit the sun, but Venus rotates in the opposite direction, a phenomenon called retrograde rotation. No one knows exactly why. It may have been knocked off course by a massive impact early in its history, or it could be due to tidal effects from the sun. Whatever the cause, it means the sun rises in the west on Venus and sets in the east. Venus is also tilted very slightly, so its seasons are minimal. It's a slow, backward world, spinning against the flow of the solar system. Uranus rotates on its side. While most planets have a slight tilt, Uranus is tilted over 90 degrees, meaning it essentially rolls along its orbital path. Its poles point toward and away from the sun during its 84-year orbit, leading to extreme seasonal variations. For part of the year, one pole is in constant sunlight, while the other is in darkness. Then, decades later, the situation reverses. Scientists think Uranus was knocked over by a massive collision early in its history. It's a strange, lopsided world, spinning in a way no other planet does, a reminder that violence shaped the solar system. Neptune has the fastest winds in the solar system. Wind speeds on Neptune can exceed 1,200 miles per hour, faster than the speed of sound on Earth. These winds blow in the opposite direction of the planet's rotation, and scientists aren't entirely sure what drives them. Neptune is far from the sun and receives very little solar energy, yet its atmosphere is incredibly active. It has dark spots, storms that come and go, and high-altitude clouds of methane ice. Neptune is dynamic and turbulent, a blue giant with winds that scream through its skies, unseen and unstoppable. The great dark spot on Neptune has disappeared. When Voyager 2 flew by Neptune in 1989, it observed a large storm called the Great Dark Spot, similar to Jupiter's Great Red Spot. But when the Hubble Space Telescope looked at Neptune a few years later, the spot was gone. It had simply vanished. Other dark spots have appeared and disappeared since then, suggesting that Neptune's atmosphere is constantly changing. Unlike Jupiter's long-lived storms, Neptune's weather is more fleeting, a reminder that even giant planets have moods, and that storms, no matter how large, eventually pass. There's a hexagon-shaped storm on Saturn's North Pole. Saturn has a peculiar feature at its North Pole, a massive hexagonal jet stream that has been observed for decades. The hexagon is about 20,000 miles across, large enough to fit 4 Earths inside. The sides are remarkably straight and the shape is stable, maintaining its form despite the swirling clouds. Scientists think it's caused by the interaction of different wind speeds, but the exact mechanism isn't fully understood. It's one of the strangest weather patterns in the solar system, a geometric shape carved into the clouds of a gas giant. Io is covered in sulfur. Io, the innermost of Jupiter's large moons, is the most volcanically active body in the solar system. Its surface is covered in sulfur and sulfur dioxide, giving it a yellow, orange, and red appearance. Lava lakes, towering plumes, and fresh lava flows constantly reshape the surface. There are no impact craters on Io because they're quickly covered by new volcanic material. The moon is squeezed and stretched by Jupiter's immense gravity, generating enough heat to keep its interior molten. Io is a world of fire, a moon constantly renewing itself, a landscape of eternal eruption. Ganymede is the largest moon in the solar system. Ganymede, another moon of Jupiter, is even larger than the planet Mercury. It's the only moon known to have its own magnetic field, suggesting it has a liquid iron core. Ganymede also has a subsurface ocean of liquid water, sandwiched between layers of ice. Its surface is a mix of old, dark terrain, covered in craters and younger, brighter regions with grooves and ridges. Ganymede is a complex world, half ice, half rock, with a hidden ocean and a magnetic shield, a moon that's almost a planet in its own right. Callisto is one of the most heavily cratered objects in the solar system. Callisto, the outermost of Jupiter's 4 large moons, has an ancient surface covered in impact craters. Some of these craters are billions of years old, a record of the early solar system when impacts were common. Unlike Io or Europa, Callisto shows little sign of geological activity. Its surface is ice and rock, cold and unchanged. Beneath the surface, there may be a subsurface ocean, but the surface itself is a frozen museum, a snapshot of the past, pockmarked by time and violence. There are asteroids with moons. Some asteroids are large enough to have their own satellites, smaller rocks that orbit them. These binary asteroids are more common than once thought. The asteroid Ida, for example, has a tiny moon named Dactyl, only about a mile across. These moons form from collisions, debris from impacts that settles into orbit rather than escaping or falling back. Studying asteroid moons helps scientists understand how objects interact in space, how gravity works on small scales, and how the solar system evolved. Even the smallest bodies can have companions, tiny worlds orbiting tiny worlds. Ceres is a dwarf planet in the asteroid belt. Ceres is the largest object in the asteroid belt and the only dwarf planet in the inner solar system. It's round, unlike most asteroids, and it may have a subsurface ocean of liquid water. Ceres has bright spots on its surface, deposits of salt left behind by water that evaporated from below. It's a frozen world, but it may have been geologically active in the past. Ceres is a bridge between asteroids and planets, a dwarf world that holds clues to the early solar system and the distribution of water in space. Vesta is one of the largest asteroids. Vesta is the second largest object in the asteroid belt, after Ceres. It has a differentiated interior, meaning it has a core, mantle, and crust, like a planet. Vesta also has a massive impact crater near its south pole, so large it nearly destroyed the asteroid. Debris from this impact has fallen to Earth as meteorites, allowing scientists to study Vesta's composition directly. Vesta is a protoplanet, a world that started to form but never grew large enough to become a full planet. It's a window into the early solar system, a survivor from the age of formation. The Kuiper Belt is home to thousands of icy worlds. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies, dwarf planets, and comets. Pluto is the most famous resident, but there are many others, like Eris, Makemake, and Haumea. These objects are leftovers from the formation of the solar system, frozen and distant, barely touched by the sun's warmth. The Kuiper Belt is like the asteroid belt, but much larger and made of ice instead of rock. It's a frontier, a realm of cold and darkness, where the sun is just a bright star and the solar system fades into the void. Pluto's largest moon, Charon, is so big it doesn't orbit Pluto. Instead, the two orbit a point in space between them, called a barycenter. Charon is about half the size of Pluto, making it the largest moon relative to its planet in the solar system. The two are tidally locked, always showing the same face to each other. From Pluto, Charon hangs motionless in the sky. From Charon, Pluto does the same. They're more like a binary system than a planet and moon, two worlds locked in an eternal dance, circling each other at the edge of the solar system. There's a planet made mostly of water. GJ 1214b is an exoplanet that may be covered in a deep ocean of water. It's larger than Earth but smaller than Neptune, and its density suggests it's made mostly of water and gas. If so, the ocean could be hundreds of miles deep, far deeper than anything on Earth. The pressure at this bottom would be immense, creating exotic forms of ice that exist only in extreme conditions. This water world is unlike anything in our solar system, a planet where the ocean has no floor, where water extends from the atmosphere to the core, a world drowned in liquid. Some planets are so hot that metal evaporates on their surface. Hot Jupiters are gas giants that orbit very close to their stars, sometimes closer than Mercury is to the Sun. On these planets, temperatures can exceed 4,000 degrees Fahrenheit. At those temperatures, metals like iron and titanium can vaporize and form clouds. The atmosphere can have winds that reach thousands of miles per hour, carrying vaporized metal from the day side to the night side, where it condenses and rains back down. These planets are alien beyond imagination, worlds of molten skies and metal rain, where the very air glows with heat. There's a planet that's darker than coal. Tres 2b is the darkest exoplanet ever discovered, reflecting less than 1% of the light that hits it. It's a hot Jupiter, tidally locked to its star, with one side always facing the sun. The planet is so hot that it glows faintly with its own heat, a dull red like a burning ember. But it absorbs almost all the light from its star, making it darker than charcoal or black paint. Scientists aren't sure why it's so dark. It may be due to chemicals in the atmosphere that absorb light, It's a shadow planet, a dark sphere orbiting close to a bright star, nearly invisible. Some planets orbit so close to their stars that their years last only hours. WASP 12b orbits its star in just over 1 Earth day. The planet is so close that it's being torn apart by the star's gravity, stretched into an egg shape. Material from the planet's atmosphere is being pulled away, forming a disk around the star. The planet is doomed. In about 10 million years, it will be completely consumed. For now, it hangs on, a world on the edge of destruction, circling its star in a desperate, losing battle against gravity. There's a star that's cooler than a campfire. The coolest known star, WISE 0855-0714, has a surface temperature of about minus 10 degrees Fahrenheit. That's colder than the freezing point of water, colder than a winter day. It's a brown dwarf, a failed star that never got hot enough to fuse hydrogen. It glows very faintly in infrared, invisible to the naked eye. It's more like a giant planet than a star, slowly cooling over billions of years. It's a reminder that stars come in all sizes and temperatures, and some barely shine at all. Red dwarfs can live for trillions of years. Red dwarfs are the smallest and coolest true stars, but they're also the longest lived. They burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. In fact, no red dwarf has ever died. The universe isn't old enough. All the red dwarfs that have ever formed are still shining, still burning, still young, in the distant future. When all the larger stars have burned out, red dwarfs will be the only stars left, tiny embers glowing in an otherwise dark universe. Blue giants burn bright and die young. At the opposite end of the spectrum, blue giants are massive, hot stars that burn through their fuel quickly. They can be tens or even hundreds of times the mass of the sun, and they shine with incredible brightness. But they only live for a few million years before exhausting their fuel and exploding as supernovae. Blue giants are the rock stars of the universe, brilliant and short-lived, burning with intensity that can't last. When they die, they seed the cosmos with heavy elements, the building blocks of planets and life. Some stars pulsate like beating hearts. Variable stars change in brightness over time, and some do so very regularly. Cepheid variables, for example, pulse brighter and dimmer over a period of days or weeks. This pulsation is caused by the star expanding and contracting, like a beating heart. The period of pulsation is directly related to the star's luminosity, which makes cepheids incredibly useful for measuring distances in space. By watching how a cepheid pulses, astronomers can determine how far away it is. These stars are cosmic yardsticks, the rhythmic beating helping us map the universe. Binary stars orbit each other. Many stars don't live alone. About half of all stars are part of binary or multiple star systems, where two or more stars orbit a common center of mass. Some binaries are close, orbiting each other in days or hours. Others are far apart, taking centuries to complete an orbit. In some cases, the stars are so close they touch, sharing material between them. Binary stars can be difficult to study because they're often too close together to see separately, but they teach us about stellar evolution, gravity, and the dynamics of orbiting bodies. Some stars explode more than once. Certain stars can undergo multiple eruptions. A nova occurs when a white dwarf in a binary system pulls material from its companion. The material builds up on the white dwarf's surface until it ignites in a thermonuclear explosion. The explosion doesn't destroy the star, just blows off the outer layers. Over time, the process can repeat, creating a recurrent nova. Some stars have been observed to explode multiple times, decades or centuries apart. They're not dead yet. They're just unstable, cycling between calm and catastrophe. Supernova can trigger new star formation. When a massive star explodes in a supernova, the shock wave it creates can compress nearby clouds of gas and dust, triggering them to collapse and form new stars. In this way, the death of one star can give birth to many others. Supernova remnants are often surrounded by regions of active star formation, bright, young stars emerging from the debris of their predecessor. It's a cycle of death and rebirth, a chain reaction that continues across the galaxy, one generation of stars, giving rise to the next. The universe is filled with invisible light. When we look at the night sky, we see only visible light. But there's much more out there. The universe glows in radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Each wavelength reveals different phenomena. Radio waves show cold gas and distant quasars. Infrared reveals heat and dust. X-rays show hot gas and black holes. By observing in multiple wavelengths, astronomers can see the full picture, the universe in all its complexity. We're surrounded by light we can't see, a symphony of radiation singing in frequencies beyond our perception. Gravitational waves ripple through space and time. When massive objects like black holes or neutron stars collide, they create ripples in space-time called gravitational waves. These waves travel at the speed of light, stretching and squeezing space as they pass. They were predicted by Einstein over a century ago, but only detected in 2015. Since then, we've detected dozens of gravitational wave events, each one a violent collision in a distant corner of the universe. These waves carry information about the most extreme events in the cosmos, moments when space itself rings like a bell. Time travel to the future is possible. According to Einstein's theory of relativity, if you travel at speeds close to the speed of light, time slows down for you relative to everyone else. If you traveled to a nearby star and back at near light speed, you might age only a few years, while decades or centuries pass on Earth. This effect has been confirmed with atomic clocks on fast-moving planes and satellites. Time dilation is real. You could travel to the future just by going very fast. The only problem is getting up to that speed, which requires enormous amounts of energy. But in theory, time travel to the future is possible. We just need to go fast enough. There may be parallel universes. Some interpretations of quantum mechanics and cosmology suggest that our universe might be one of many, perhaps infinitely many, each with different physical laws, constants, or histories. These parallel universes, or the multiverse, would be completely separate from ours, impossible to reach or observe. It's a speculative idea, more philosophy than science at this point. But some theories, like eternal inflation, predict it. If the multiverse is real, then everything that can happen does happen, somewhere, in some version of reality. It's a strange and dizzying thought, that we might be just one universe among countless others, all existing side by side, forever apart. The universe might be a simulation. Some physicists and philosophers have seriously considered the idea that our reality could be a computer simulation created by an advanced civilization. The argument goes that if it's possible to create realistic simulations, and if civilizations tend to create many simulations, then statistically, we're more likely to be living in a simulation than in base reality. It's impossible to prove or disprove, but it's a fascinating thought experiment. If the universe is a simulation, would it change anything? Would the stars be less beautiful? Would your experiences be less real? Perhaps not. Perhaps reality is what we make of it, simulated or not. You are made of stardust. The atoms in your body were forged in the cores of stars. The carbon, oxygen, nitrogen, and other elements that make up your cells were created billions of years ago in stellar furnaces and scattered into space when those stars died. Those atoms drifted through the galaxy, eventually coming together to form the sun, the earth, and you. You're not separate from the universe. You're a part of it, a temporary gathering of stardust that has become aware, capable of looking back at the stars and recognizing your origin. In a very real sense, you are the universe experiencing itself. The sun loses mass constantly. Every second, the sun converts about 4 million tons of matter into energy through nuclear fusion. This mass is radiated away as light and heat. Over the course of the sun's lifetime, it has lost a significant amount of mass, but it's so enormous that the loss is negligible. The sun will continue burning for another 5 billion years, slowly losing mass, slowly dimming until it finally runs out of fuel. But for now, it shines steadily, a constant source of light and warmth, anchoring the solar system with its gravity. There are planets that rain glass sideways. On the exoplanet HD 189733b, winds can reach 5,000 to 400 miles per hour, and the atmosphere contains silicate particles that condense into glass. Extreme winds blow this glass horizontally at supersonic speeds. The planet is tidally locked, with one side always facing its star. The day side is scorching hot, while the night side is cooler. This temperature difference drives the fierce winds. Standing on this planet, if you could survive, you'd be sandblasted by molten glass flying sideways faster than the speed of sound. It's a world of beautiful blue color and deadly weather. Some galaxies have no dark matter. Most galaxies are held together by dark matter, the invisible substance that provides extra gravitational pull. But astronomers have discovered a few galaxies that seem to have little or no dark matter. One example is NGC 1052 DF2, a diffuse galaxy where the stars move at speeds that match the visible matter alone. Scientists aren't sure how these galaxies formed or why they lack dark matter. It challenges our understanding of galaxy formation and the role of dark matter in the universe. These galaxies are anomalies, exceptions to the rule, mysteries waiting to be solved. The Hubble Space Telescope has taken over 1 million observations. Since its launch in 1990, Hubble has been one of the most productive scientific instruments ever built. It has observed distant galaxies, nebulae, planets, stars, and countless other objects. Its images have become iconic, showing the universe in stunning detail. Hubble orbits Earth above the atmosphere, which allows it to capture images without the blurring effect of air. It has helped determine the age of the universe, discovered moons around Pluto, and observed galaxies from when the universe was young. Hubble has changed how we see the cosmos, one image at a time. The James Webb Space Telescope can see the first galaxies. Launched in 2021, the James Webb Space Telescope is designed to look deeper into space and further back in time than any telescope before it. It observes in infrared, which allows it to see through dust and detect the light from the very first stars and galaxies. Webb has already sent back stunning images of distant galaxies, star-forming regions, and exoplanet atmospheres. It's helping astronomers understand how galaxies formed, how stars are born, and what the atmospheres of other worlds are made of. Webb is opening new windows into the universe, revealing secrets that have been hidden since the beginning of time. There are galaxies shaped like jellyfish. Some galaxies, when passing through the hot gas in galaxy clusters, have their gas stripped away by a process called ram pressure stripping. This creates long tails of gas and stars trailing behind the galaxy, making it look like a jellyfish swimming through space. These jellyfish galaxies are losing the material they need to form new stars, and over time, they may become passive, filled only with old stars. The tails are regions of intense star formation, bright and active, a final burst of light before the galaxy quiets down. They're beautiful and tragic, galaxies being slowly dismantled by their environment. The Andromeda Galaxy contains 1 trillion stars. Andromeda is the nearest large galaxy to the Milky Way and is significantly larger. While the Milky Way has about 200 to 400 billion stars, Andromeda has about 1 trillion. It's also more massive, with more dark matter holding it together. When you look at Andromeda, even with the naked eye, you're seeing the combined light of 1 trillion suns, a vast island of stars stretching across hundreds of thousands of light years, and it's coming closer. In a few billion years, the two galaxies will merge, combining their stars into one giant elliptical galaxy. There are stars that have planets older than Earth. The universe is 13.8 billion years old, and Earth is only 4.5 billion years old. That means there are stars and planets that formed billions of years before our solar system. Some of these ancient planets have been around for 10 billion years or more. If life emerged on any of these worlds, it would have had billions of years more time to evolve than life on Earth. It's possible that advanced civilizations existed and died long before our sun was even born. The universe is old enough for entire histories to have played out in the deep past. Civilizations will never know. Stories lost to time. The Great Attractor is pulling our galaxy toward it. The Milky Way, along with thousands of other galaxies, is being pulled toward a region of space called the Great Attractor. It's a gravitational anomaly, a concentration of mass so large that it affects the motion of galaxies millions of light years away. We can't see the Great Attractor directly because it's hidden behind the plane of the Milky Way, obscured by dust and stars. But we can measure its effect on the motion of galaxies. Something massive is out there, pulling us toward it, and we're moving at about 600 kilometers per second. We won't reach it for billions of years, but we're on our way. There's a massive void in space called the Boötes Void. The Boötes Void is one of the largest known voids in the universe, a region about 330 million light-years across that contains very few galaxies. Most of the universe is organized into a web-like structure, with galaxies clustered along filaments and large empty spaces in between. But the Boötes Void is unusually empty, containing only about 60 galaxies in a space that would typically hold thousands. It's a vast, dark region, a bubble of emptiness in the cosmic web. Standing in the middle of the Boötes Void, the night sky would be almost completely dark, with only a handful of faint galaxies visible. Some stars have been ejected from the Milky Way. Hypervelocity stars are stars moving so fast that they're escaping the galaxy entirely. They can reach speeds of over 1,000,000 miles per hour, fast enough to break free of the Milky Way's gravity. These stars were likely flung out by interactions with the supermassive black hole at the galaxy's center, or by the explosion of a companion star in a binary system. Once ejected, they travel through intergalactic space, lone wanderers leaving the galaxy behind. It's a lonely fate to be cast out into the void, forever separated from the galaxy that gave you birth. The cosmic web connects everything. On the largest scales, the universe is organized into a web-like structure. Galaxies are not randomly scattered. They cluster along vast filaments of dark matter, with enormous voids in between. Where filaments intersect, you find superclusters, the largest gravitationally bound structures in the universe. This cosmic web spans billions of light years, a delicate tracery of matter stretched across the void. It formed from tiny fluctuations in the early universe, seeds of structure that grew over billions of years. The web is the skeleton of the universe, the framework on which everything else is built. Quasars are the brightest objects in the universe. Quasars are powered by supermassive black holes at the centers of distant galaxies. As matter falls into the black hole, it heats up and emits enormous amounts of energy, sometimes outshining the entire galaxy. Quasars are so bright they can be seen from billions of light years away. They were more common in the early universe, when galaxies were younger and more gas was available to feed the black holes. Today, quasars are rare, but in the distant past, they lit up the cosmos like cosmic lighthouses. Looking at quasars is looking back to a time when the universe was wilder, more violent, and far more active. Some black holes are supermassive. At the center of most galaxies, including the Milky Way, lies a supermassive black hole. These black holes can be millions or even billions of times the mass of the Sun. The one at the center of our galaxy, Sagittarius AQ, is about 4 million solar masses. Despite their enormous mass, supermassive black holes are not constantly feeding. They can remain dormant for long periods, only flaring up when gas or stars fall into them. When they do feed, they can power quasars and active galactic nuclei, some of the most energetic phenomena in the universe. These black holes are ancient, likely forming in the early universe and growing over billions of years. There are stars so large they could fit the orbit of Jupiter inside them. The largest known stars are red supergiants, bloated and cool, nearing the end of their lives. Stars like UY Scuti or Stephenson 218 are so enormous that if you place them at the center of our solar system, their surface would extend beyond the orbit of Jupiter. These stars are hundreds of times the diameter of the Sun. They're also unstable, losing mass through powerful stellar winds. Eventually, they'll explode as supernovae, collapsing into neutron stars or black holes. For now, they shine dim and red, giants slowly dying in the cold of space. Some stars are so small they barely shine at all. Red dwarfs, the smallest true stars, are only slightly larger than Jupiter. The smallest known star, EBLM J0555, 57AB, is about the size of Saturn. It's barely massive enough to sustain hydrogen fusion, the process that makes stars shine. If it were any smaller, it would be a brown dwarf, a failed star. Red dwarfs are faint and cool, shining with a dim red light. But they're the most common type of star in the universe, making up about 70% of all stars. They're small, quiet, and incredibly long-lived, the silent majority of the stellar population. Galaxies can have supermassive black holes that are billions of times the mass of the Sun. The most massive black holes known are tens of billions of solar masses. TON 618, for example, has a black hole about 66 billion times the mass of the Sun. Its event horizon is so large it would stretch hundreds of times the distance from the Sun to Pluto. These ultra-massive black holes are rare, found in the most massive galaxies. How they grew so large is still a mystery. They may have formed from the merger of many smaller black holes, or they may have had a head start, forming from massive seeds in the early universe. There are galaxies colliding right now. Galaxy collisions are common in the universe. When galaxies collide, they don't crash like solid objects. Instead, they pass through each other, their stars rarely colliding because space is so vast. But the gravitational interactions distort both galaxies, triggering bursts of star formation and feeding the central black holes. Over hundreds of millions of years, the galaxies merge, forming a single, larger galaxy. The antenna galaxies and the mice galaxies are examples of ongoing collisions, their shapes warped and stretched by gravity. Watching galaxies collide is like watching continents drift, a slow-motion dance that reshapes the cosmos. The Milky Way has consumed other galaxies. The Milky Way has grown over billions of years by absorbing smaller galaxies. Streams of stars in the outer halo are remnants of these past mergers, torn from their original galaxies, and now orbiting the Milky Way. The Sagittarius dwarf galaxy is currently being torn apart and absorbed. Its stars are being stretched into a long stream that wraps around the Milky Way. This process of galactic cannibalism is how large galaxies grow. The Milky Way is a graveyard, filled with the remnants of smaller galaxies, their stars now part of our own. Some planets orbit in the habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Earth is in the Sun's habitable zone, which is why we have liquid oceans. Astronomers have discovered many exoplanets in habitable zones around other stars. Some are rocky, like Earth. Others are larger, called super-Earths. Whether any of these planets have liquid water, atmospheres, or life is still unknown. But the search continues, looking for worlds that might be homes to life. Worlds where the conditions are just right. There are more Earth-sized planets than any other type. Early exoplanet discoveries favored large planets because they were easier to detect. But as technology improved, astronomers found that small, rocky planets are actually the most common. The galaxy is filled with worlds similar in size to Earth, orbiting stars of all types. Many of these planets are too close to their stars to be habitable, scorched by heat. Others are too far, frozen and dark, but some are in the right place, in the habitable zone, with the right temperature for liquid water. The universe may be full of Earth-like worlds, quiet and waiting, some of them perhaps alive. We have sent messages into space. In the 1970s, the Voyager spacecraft were launched with golden records attached, containing sounds and images from Earth. The records include greetings in many languages, music, natural sounds, and pictures. They're messages in a bottle, sent into the cosmic ocean. Voyager 1 has now left the solar system and is traveling through interstellar space. In tens of thousands of years, it may pass near another star. If any intelligent beings find it, the golden record will tell them about us. a snapshot of humanity frozen in time. The Voyagers carry our voice into the stars, a message that says, "We were here." The Fermi paradox asks, "Where is everyone?" The universe is vast and old. There are billions of stars and planets. The conditions for life seem to be common. So, where are all the aliens? This is the Fermi paradox. If life is common, we should see evidence of it. Radio signals, spacecraft, megastructures. But we've found nothing. Maybe life is rarer than we think. Maybe civilizations destroy themselves. Maybe they're out there but too far away, or too different, or simply not interested in contacting us. The silence is puzzling. The universe seems empty, but perhaps we're just not listening in the right way, or at the right time. SETI searches for signals from other civilizations. The search for extraterrestrial intelligence uses radio telescopes to listen for signals from space. The idea is that advanced civilizations might broadcast radio waves, either intentionally or as a byproduct of their technology. SETI has been listening for decades, scanning millions of frequencies and thousands of stars. So far, they've found nothing conclusive. A few interesting signals, but nothing that clearly comes from intelligent life. The search continues, patient and hopeful, listening to the stars, waiting for a message that might never come, or might come tomorrow. The WOW signal remains unexplained. In 1977, a radio telescope in Ohio detected a strong signal from space that lasted 72 seconds. It was so unusual that the astronomer on duty wrote "wow" next to the data. The signal had all the hallmarks of an artificial transmission, but it was never detected again. It came from the direction of the constellation Sagittarius, but no star or planet in that region could explain it. Decades later, the WOW signal remains a mystery. It might have been a natural phenomenon, or it might have been something else, a brief glimpse of something we've been searching for, or just a cosmic fluke. Mars might have had life in the past. Mars was once warmer and wetter, with rivers, lakes, and possibly oceans. The conditions might have been right for life to emerge. Rovers on Mars have found evidence of ancient water and organic molecules, the building blocks of life. But whether life actually existed is still unknown. If it did, it was probably simple, microbial life. Some scientists think life might still exist underground in pockets of liquid water beneath the surface. Mars is a cold, dry desert now, but it holds clues to its past, and perhaps to the question of whether life can arise elsewhere in the universe. Europa's ocean might harbor life. Europa, a moon of Jupiter, has a thick shell of ice covering a global ocean of liquid water. The ocean is kept warm by tidal heating, the same process that makes Io volcanic. Where there's liquid water, there might be life. On Earth, life thrives in extreme environments, deep under the ice, near volcanic vents, in total darkness. Europa's ocean could be similar, a hidden world beneath the ice, perhaps home to simple organisms. Future missions may drill through the ice to explore the ocean and search for signs of life. Europa is one of the best places in the solar system to look for extraterrestrial life. Enceladus shoots water into space. Enceladus, a small moon of Saturn, has geysers that erupt from cracks near its south pole, shooting water and ice particles hundreds of miles into space. This water comes from a subsurface ocean, and it contains organic molecules and salts. The Cassini spacecraft flew through these plumes and analyzed their composition. The findings suggest that Enceladus has the ingredients for life: liquid water, organic molecules and a source of energy. Like Europa, Enceladus is a prime target in the search for life beyond Earth. Its ocean is hidden, but the geysers bring samples directly to us, making it easier to study. Titan has lakes, rivers, and rain. Titan, Saturn's largest moon, is the only place in the solar system besides Earth with stable liquid on its surface. But instead of water, Titan's lakes are made of liquid methane and ethane. The moon has a thick atmosphere, weather, and a hydrological cycle, with methane evaporating, forming clouds, and raining back down. Titan is cold, about minus 290 degrees Fahrenheit, which allows methane to exist as a liquid. It's an alien world, but one with familiar processes, a place where the chemistry is different, but the patterns are the same. Titan might even have life, organisms adapted to the cold and the methane lakes. Venus might have had oceans for billions of years. Venus is now a hellish world, with surface temperatures hot enough to melt lead and an atmosphere thick with carbon dioxide. But billions of years ago, Venus might have been more like Earth, with liquid water on its surface. Computer models suggest Venus could have had oceans for 2 to 3 billion years before a runaway greenhouse effect boiled them away. If so, Venus might have been habitable in the distant past, perhaps even home to life. Now it's a cautionary tale, a world that lost its water and became an inferno. Venus reminds us that planets can change, and not always for the better. Mercury has water ice in permanently shadowed craters. Despite being the closest planet to the Sun, Mercury has water ice at its poles. The planet's axis is nearly vertical, which means some craters near the poles never see sunlight. These permanently shadowed regions are cold enough for ice to survive. Radar observations and data from the Messenger spacecraft confirmed the presence of water ice, likely delivered by comets. Mercury is a world of extremes, scorching hot in sunlight, freezing cold in shadow. It's a reminder that even the most unlikely places can hold surprises. The asteroid belt could have formed a planet. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky debris. If all the material in the asteroid belt were combined, it would form a small planet, but it never did. Jupiter's gravity prevented the asteroids from coalescing, stirring them up and causing collisions instead of gentle mergers. The asteroid belt is what's left over from the formation of the solar system, a failed planet, scattered remnants that never came together. It's a reminder that planet formation is messy, and not every region of a solar system gets a planet. Jupiter protects Earth from asteroids. Jupiter is so massive that its gravity influences the orbits of comets and asteroids. It can fling them out of the solar system or pull them in, preventing many from reaching the inner planets. Jupiter acts like a cosmic shield, reducing the number of impacts on Earth. Without Jupiter, Earth would be hit by asteroids more often, making life more difficult. We owe a debt to Jupiter, the giant planet that quietly protects us, deflecting dangers we never see. Saturn's rings are disappearing. Saturn's rings are made of ice and rock, and they're slowly falling into the planet. The rings are being pulled down by Saturn's gravity, raining onto the planet as icy particles. At the current rate, the rings could disappear in about 100 million years. That might sound like a long time, but in cosmic terms, it's brief. Saturn hasn't always had rings, and it won't always have them. We're fortunate to live at a time when Saturn still wears its spectacular crown, a temporary adornment that will one day be gone. Uranus and Neptune are ice giants, while Jupiter and Saturn are gas giants, made mostly of hydrogen and helium. Uranus and Neptune are ice giants, with more water, methane, and ammonia in their interiors. These compounds were ice in the cold outer solar system when the planets formed, which is why they're called ice giants, even though the material is actually in a hot, dense fluid state. Uranus and Neptune are blue because of methane in their atmospheres, which absorbs red light. They're distant, cold worlds, rarely visited by spacecraft, but they hold clues to how planets form in the outer reaches of solar systems. There's a ninth planet hiding beyond Neptune. Some astronomers believe there's a large planet, perhaps 10 times the mass of Earth, orbiting in the far outer solar system. This hypothetical Planet 9 hasn't been observed directly, but its existence could explain the unusual orbits of some distant objects in the Kuiper Belt. If Planet 9 exists, it's far away, cold and dark, taking thousands of years to orbit the Sun. The search continues, using telescopes to scan the sky for a faint, slow-moving object. If it's out there, it would be a major discovery, a hidden world at the edge of the solar system. Comets are time capsules. Comets are leftovers from the formation of the solar system, preserved in the cold outer reaches. They contain pristine ice and dust, unchanged for 4.5 billion years. When we study comets, we're looking at material from the solar system's birth. Comets may have brought water and organic molecules to Earth, seeding the planet with the ingredients for life. They're messengers from the past, carrying information about the early solar system, about the conditions that existed when the planets were forming. Each comet is a frozen archive, a piece of history traveling through space. The Sun is middle-aged. The Sun is about 4.6 billion years old, roughly halfway through its life. In another 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium. It will swell into a red giant, expanding to engulf Mercury and Venus. Earth will be scorched, its oceans boiled away, its surface lifeless. The Sun will shed its outer layers, forming a planetary nebula, leaving behind a white dwarf. That white dwarf will slowly cool over trillions of years, fading to black. But for now, the Sun is stable, shining steadily in the prime of its life, and the solar system is moving through the galaxy. The Sun, along with all the planets, is orbiting the center of the Milky Way at about 515,000 miles per hour. It takes the solar system about 230 million years to complete one orbit, a period called a galactic year. The last time the Sun was in this position, dinosaurs were just beginning to appear on Earth. One galactic year from now, if the Earth still exists, it will be in a completely different era. The solar system is always moving, tracing a spiral path through the galaxy, never returning to the same place twice. The Sun will eventually become a white dwarf. When the Sun runs out of fuel, it will shed its outer layers, creating a planetary nebula. The core that remains will be a white dwarf, a hot, dense object about the size of Earth. It will no longer produce energy through fusion. It will just radiate away its stored heat, cooling over billions of years. Eventually, it'll become a black dwarf, a cold, dark cinder. But the universe isn't old enough for any black dwarfs to exist yet. The Sun's white dwarf will glow faintly for trillions of years, a quiet echo of the star it once was. Some stars end as neutron stars. When a massive star explodes in a supernova, the core can collapse into a neutron star, an object so dense that protons and electrons combine into neutrons. Neutron stars are about 12 miles across, but contain more mass than the Sun. They spin rapidly, sometimes hundreds of times per second, and have magnetic fields trillions of times stronger than Earth's. Some neutron stars emit beams of radiation, making them pulsars. Neutron stars are the densest objects in the universe that we can observe, and they challenge our understanding of physics, pushing matter to its limits. Some stars end as black holes. If a star is massive enough, more than about 20 times the mass of the Sun, it will collapse into a black hole when it dies. The core collapses so completely that nothing can stop it. It becomes a singularity, a point of infinite density, surrounded by an event horizon, the point of no return. Black holes don't emit light, so they're invisible, but we can detect them by their effects on nearby matter. They pull in gas, which heats up and glows brightly before falling in. Some black holes are in binary systems, orbiting normal stars, slowly consuming them. Black holes are the final fate of the most massive stars, regions where gravity wins absolutely. There are rogue black holes wandering the galaxy. Not all black holes sit quietly at the centers of galaxies. Some were ejected from their birthplaces by gravitational interactions or the recoil from mergers. These rogue black holes wander through interstellar space, invisible and alone. They're nearly impossible to detect unless they pass in front of a star or pull on nearby gas. But they're out there, silent travelers, moving through the dark. If one passed near the solar system, it could disrupt the orbits of planets, though the chances of that happening are incredibly small. Rogue black holes are the universe's wanderers, untethered and free. Black holes evaporate over time. According to Stephen Hawking, black holes are not entirely black. They emit a faint radiation called Hawking radiation, caused by quantum effects near the event horizon. This radiation carries away energy, causing the black hole to slowly lose mass. Over an unimaginably long time, trillions of years, a black hole will evaporate completely, ending in a final burst of energy. The smaller the black hole, the faster it evaporates. Stellar mass black holes will take longer than the current age of the universe, many times over, to evaporate. But eventually, even black holes die, fading into the quantum foam from which they came. The pillars of creation are a star nursery. In the Eagle Nebula, about 6,500 light-years away, there are towering columns of gas and dust called the pillars of creation. These pillars are several light-years tall, and inside them, new stars are being born. The gas is dense enough to collapse under gravity, forming protostars that will eventually ignite. The Hubble Space Telescope captured iconic images of these pillars in 1995, and they've become one of the most recognizable images in astronomy. But the pillars may already be gone. A nearby supernova may have destroyed them thousands of years ago. We won't know for another 1,000 years when the light from that destruction finally reaches us. The Orion Nebula is visible to the naked eye. On a clear winter night in the northern hemisphere, you can see the Orion constellation. In the middle of Orion's sword, there's a fuzzy patch of light. That's the Orion Nebula, a massive cloud of gas and dust where new stars are forming. It's about 1,344 light-years away and about 24 light-years across. Inside the nebula, thousands of stars are being born, some already visible, others still hidden in their dusty cocoons. The Orion Nebula is one of the closest star-forming regions to Earth, which makes it a valuable laboratory for studying how stars and planets form. And you can see it without a telescope, a stellar nursery visible to the naked eye. The Crab Nebula is a supernova remnant. In 1054 AD, Chinese astronomers recorded a bright new star in the sky. It was visible during the day for weeks. What they saw was a supernova, a star exploding. Today, we can see the remnants of that explosion, the Crab Nebula. It's an expanding cloud of gas and debris, glowing from the energy of the explosion. At the center is a pulsar, a rapidly spinning neutron star that emits beams of radiation. The Crab Nebula is still expanding, growing larger year by year. It's one of the most studied objects in astronomy, a window into the violent death of a massive star. The Horsehead Nebula is a dark cloud. The Horsehead Nebula is a dark nebula, a cloud of dust so dense that it blocks the light from stars behind it. It's located in the constellation Orion, and it's shaped like a horse's head, hence the name. The nebula is part of a larger cloud complex, and inside it, stars are forming. Dark nebulae are cold and dense, the perfect environment for star formation. The Horsehead Nebula is about 1,500 light-years away and about 3.5 light-years across. It's one of the most photographed objects in the night sky, a silhouette against a glowing background, a shadow shaped like a dream. The Ring Nebula is a dying star's last breath. The Ring Nebula in the constellation Lyra is a planetary nebula, a shell of gas ejected by a dying star. The star at the center has exhausted its fuel and shed its outer layers, which are now expanding outward, glowing from the ultraviolet radiation of the hot core. The ring shape is an illusion. The nebula is actually a cylinder or barrel, and we're looking at it from the side. In a few thousand years, the gas will disperse, and the central star will fade to a white dwarf. The Ring Nebula is a preview of the Sun's fate, a glimpse of what will happen billions of years from now. The Helix Nebula is the closest planetary nebula. The Helix Nebula, also called the Eye of God, is about 650 light-years away, making it one of the closest planetary nebulae to Earth. It's the expanding shell of a sun-like star that died thousands of years ago. The nebula is large, about 2.5 light-years across, and it glows in shades of red and green. At the center is a white dwarf, the hot core of the star that remains. The Helix Nebula is beautiful and haunting, a cosmic eye staring back at us, a reminder that stars, like all things, have an end. The Butterfly Nebula has 2 lobes of gas. The Butterfly Nebula is a planetary nebula with a distinctive shape, 2 lobes of gas extending in opposite directions, like the wings of a butterfly. The star at the center is one of the hottest known, with a surface temperature over 400,000 degrees Fahrenheit. The lobes were ejected by the star in a complex process involving rotation and magnetic fields. The nebula is expanding at hundreds of kilometers per second, carrying the star's former outer layers into space. It's a beautiful and violent process, the final act of a dying star, frozen in a moment of transformation. Nebulae come in many colors. Nebulae glow in different colors depending on their composition and the energy of nearby stars. Hydrogen emits red light when excited. Oxygen emits green and blue. Sulfur emits red. Many images of nebulae use filters to capture these specific wavelengths, then assign them colors to create stunning false color images. In reality, Most nebulae would appear faint and grayish to the human eye because they're so dim, but with long exposures and color filters, telescopes reveal the hidden beauty, the intricate structures and glowing gases that fill the space between stars. Nebulae are the universe's art galleries, canvases painted with light and gas. Stars form in clusters. Most stars are born in groups, dozens or hundreds forming together in the same cloud of gas. These star clusters stay together for a while, bound by gravity, but over time they drift apart. The stars scatter across the galaxy, becoming isolated like the sun. Open clusters, like the Pleiades, contain young stars still loosely bound together. Globular clusters are older and more tightly packed, with thousands or millions of stars in a spherical swarm. The Sun was probably born in a cluster billions of years ago. Its siblings are now scattered across the galaxy, moving in different directions, forever separated. The Pleiades are a young star cluster. The Pleiades, also called the Seven Sisters, are a cluster of hot, blue stars in the constellation Taurus. They're visible to the naked eye, and on a clear night, you can see 6 or 7 stars, though the cluster contains over 1,000. The Pleiades are young, only about 100 million years old, still surrounded by the dust and gas from which they formed. They're bright and beautiful, but they won't last. In a few 100 million years, the cluster will disperse, the stars drifting apart, each going its own way. The Pleiades are a brief moment of togetherness in the long life of the galaxy. Globular clusters are ancient. Globular clusters are spherical collections of old stars, tightly packed and bound by gravity. They orbit the outskirts of galaxies, and some are nearly as old as the universe itself. The stars in globular clusters are metal-poor, meaning they formed before the galaxy had produced many heavy elements. They're fossils, remnants of the early universe, windows into a time when the galaxy was young. Globular clusters can contain hundreds of thousands or even millions of stars, all crowded into a relatively small space. Near the center of a globular cluster, stars are so densely packed that collisions can occur, creating exotic objects like blue stragglers and X-ray binaries. The Sun has a twin somewhere. Most stars form in pairs or groups, and the Sun likely had a companion when it was born. This hypothetical twin, sometimes called nemesis, would have been a red dwarf or brown dwarf. Over time, the two stars would have drifted apart, scattered by gravitational interactions with other stars or the galaxy itself. The Sun's twin is now lost, somewhere in the Milky Way, orbiting the galaxy on a different path. We may never find it. It could be anywhere, indistinguishable from billions of other stars. But it's out there, the Sun's long-lost sibling, a ghost from the past. Binary stars can eclipse each other. In some binary systems, the stars orbit in a plane that aligns with our line of sight. When one star passes in front of the other, it blocks the light, causing the system to dim. These eclipsing binaries are valuable to astronomers because they allow precise measurements of the stars' sizes, masses, and orbits. Algol, the demon star, is a famous eclipsing binary. Every 2.87 days, the system dims as the fainter star passes in front of the brighter one. Ancient astronomers noticed Algol's changing brightness and considered it unlucky. Now, we understand it's just two stars locked in a cosmic dance. Some binary stars are so close they touch. In contact binaries, two stars orbit so close that their outer layers merge, forming a peanut-shaped object. They share a common envelope of gas, and material flows between them. These systems are unstable and will eventually merge into a single star. Before they do, they can undergo dramatic changes, including nova-like eruptions. Contact binaries are rare and short-lived, a brief phase in stellar evolution. They're reminders that stars can interact in complex and surprising ways, that the universe is full of odd couples and strange relationships. Some stars steal material from their companions. In a binary system where one star is a white dwarf, neutron star, or black hole, it can pull gas from its companion. The gas spirals inward, forming an accretion disk around the compact object. As the gas falls in, it heats up and glows, sometimes brightly enough to outshine the companion star. This process can trigger novae, sudden brightening events when accumulated gas ignites in a thermonuclear explosion. The system returns to normal, then the process repeats. These vampire stars slowly drain their companions, growing stronger as their partners weaken, a parasitic relationship written in starlight. Novae are not supernovae. A nova is a sudden brightening of a star, but it's not a supernova. Novae occur in binary systems where a white dwarf accretes material from a companion. When enough material builds up, it ignites in a thermonuclear explosion on the white dwarf's surface. The star brightens dramatically, sometimes becoming visible to the naked eye, then fades back to normal over weeks or months. The white dwarf survives, and the process can repeat. Supernovae, by contrast, are the explosive deaths of massive stars or the complete destruction of white dwarfs. Novae are dramatic, but they're not the end. The star lives to shine another day. Type Ia supernovae are cosmic standard candles. When a white dwarf in a binary system accretes enough material to reach a critical mass, about 1.4 times the mass of the Sun, it collapses and explodes. This type of supernova, called a type Ia, always happens at the same mass, so it always produces roughly the same brightness. This makes type Ia supernova useful for measuring distances in the universe. By comparing the observed brightness to the known intrinsic brightness, astronomers can calculate how far away the supernova is. This method was used to discover that the universe's expansion is accelerating, a finding that led to the Nobel Prize and the realization that dark energy exists. Supernovae can outshine galaxies. For a brief period, a supernova can be as bright as the entire galaxy it's in. A single dying star, in its final moment, releases more energy than billions of stars combined. The light from a supernova can be seen from across the universe. In 1006 AD, a supernova was visible in broad daylight, bright enough to cast shadows at night. In 1987, a supernova in the Large Magellanic Cloud was visible to the naked eye, the first naked-eye supernova in nearly 400 years. Supernovae are the universe's fireworks, spectacular and brief, lighting up the cosmos with the final blaze of a dying star. The Sun is made mostly of hydrogen and helium. About 73% of the Sun's mass is hydrogen, 25% is helium, and the remaining 2% is heavier elements like carbon, oxygen, and iron. The Sun is a giant ball of gas, held together by its own gravity, with no solid surface. In the core, hydrogen fuses into helium, releasing energy that eventually makes its way to the surface and radiates into space as light. This process has been going on for 4.6 billion years, and it will continue for another 5 billion. The Sun is ordinary, unremarkable, one of billions of similar stars. But to us, it's everything. The Sun's core is incredibly dense. The core of the Sun, where nuclear fusion occurs, is about 150 times denser than water. The temperature there is about 27 million degrees Fahrenheit. Under these extreme conditions, hydrogen nuclei collide with enough energy to overcome their repulsion and fuse together, forming helium and releasing energy. This energy slowly works its way outward, taking hundreds of thousands of years to travel from the core to the surface. By the time it reaches us, it's the sunlight we see every day, a gentle warmth that started as a violent fusion reaction deep in the Sun's heart. The Sun rotates, but not uniformly. The Sun is not a solid body, so different parts rotate at different speeds. The equator rotates faster, completing a rotation in about 25 days, while the poles take about 35 days. This differential rotation creates stress in the Sun's magnetic field, which can lead to sunspots, flares, and coronal mass ejections. The Sun's rotation has been slowing down over billions of years due to the solar wind carrying away angular momentum. It used to spin much faster when it was young. The Sun is not rigid. It's fluid, dynamic, constantly in motion. Sunspots are cooler regions on the Sun's surface. Sunspots appear dark because they're cooler than the surrounding areas, about 6,500 degrees Fahrenheit compared to 10,000 degrees. They're caused by concentrations of magnetic field that inhibit convection, preventing hot gas from rising to the surface. Sunspots come and go in an 11-year cycle, with periods of high and low activity. During solar maximum, the Sun is covered in sunspots. During solar minimum, there are few or none. The Sun is not constant. It has moods, cycles, and rhythms, a heartbeat measured in years. Solar flares are massive explosions on the Sun. Solar flares are sudden releases of energy, sometimes equivalent to millions of hydrogen bombs exploding at once. They're caused by the reconnection of magnetic field lines, which releases enormous amounts of energy in the form of light, heat, and charged particles. Flares can disrupt radio communications, damage satellites, and create auroras on Earth. Large flares can even affect power grids, causing blackouts. The Sun is capable of violence, of sudden outbursts that can reach across space and touch the Earth. It's a reminder that the Sun is not just a gentle light in the sky. It's a star, powerful and unpredictable. Coronal mass ejections can hit Earth. Coronal mass ejections are massive bursts of plasma and magnetic field ejected from the Sun. When directed at Earth, they can cause geomagnetic storms that disrupt technology and create beautiful auroras. In 1859, a massive CME called the Carrington event hit Earth, causing auroras visible as far south as the Caribbean and disrupting telegraph systems worldwide. If a similar event happened today, it could cause widespread damage to satellites, power grids, and communication systems. The Sun can reach out and touch us, for better or worse. We live in the Sun's atmosphere, in the extended reach of its influence. The solar wind is a stream of charged particles. The Sun constantly emits a stream of electrons, protons, and other particles called the solar wind. This wind flows outward from the Sun at hundreds of kilometers per second, filling the solar system. When the solar wind reaches Earth, it interacts with the magnetosphere, creating auroras and affecting space weather. The solar wind shapes the magnetospheres of planets, creates comet tails, and defines the boundary of the solar system. Beyond a certain distance, the solar wind meets the interstellar medium, forming a boundary called the heliopause. The solar wind is the Sun's breath, flowing constantly. touching everything in its reach. The heliopause is the edge of the sun's influence. The heliopause is the boundary where the solar wind meets the interstellar medium, the gas and dust between stars. It's the edge of the heliosphere, the bubble of space dominated by the sun. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Beyond the heliopause, the solar wind no longer dominates. The environment is shaped by the galaxy instead of the sun. It's the edge of home, the boundary between the solar system and the vast space beyond. But it's not a hard line. It's a gradual transition, a fading of the sun's influence as you move into the wider cosmos. The Voyager spacecraft carry golden records. In 1977, NASA launched Voyager 1 and Voyager 2 on a mission to explore the outer planets. Attached to each spacecraft is a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth. The records include greetings in 55 languages, music from various cultures, natural sounds like wind and thunder, and images of people, places, and scientific diagrams. The records are designed to last billions of years, long after the spacecraft have gone silent. They're messages to any intelligent beings who might find them, a snapshot of humanity, a voice calling out across the void, saying, "This is who we are." Voyager 1 is the farthest human-made object from Earth. Voyager 1 is now over 15 billion miles from Earth, traveling at about 38,000 miles per hour relative to the Sun. It's in interstellar space, beyond the heliopause, moving through the galaxy. It will continue traveling for tens of thousands of years, eventually passing near other stars. By then, its power source will have long since died, and it will be silent, a relic drifting through space. But the golden record will still be there, a message from a world that may no longer exist, carried by a machine built by beings who reached for the stars. Pioneer 10 and 11 carry plaques. Before Voyager, NASA launched Pioneer 10 and 11, which were the first spacecraft to visit Jupiter and Saturn. Attached to each spacecraft is a gold anodized aluminum plaque showing the location of Earth, images of a man and woman, and other information. The plaques were designed by Carl Sagan and others as messages to any extraterrestrials who might find the spacecraft. Like the Voyager golden records, the plaques are designed to last for eons. Pioneer 10 is now heading out of the solar system silent and alone, carrying its message into the galaxy. It's unlikely anyone will ever find it. But the gesture itself is meaningful, a statement that we tried to reach out, to connect. We have only explored a tiny fraction of the universe. Humans have walked on the moon, sent probes to every planet, and landed on comets and asteroids. But all of that exploration has been confined to our solar system, a tiny speck in the vastness of space. The nearest star is over 4 light-years away, and with current technology, it would take tens of thousands of years to reach it. We've sent radio signals and spacecraft carrying messages, but we haven't gone far. The universe is vast, and we've only seen the neighborhood. We're like children standing at the edge of an ocean, having only waded in the shallows, wondering what lies beyond the horizon. Interstellar travel would take generations. With current propulsion technology, traveling to another star would take tens of thousands of years. Even traveling at a significant fraction of the speed of light would take decades or centuries. One proposed solution is a generation ship, a massive spacecraft where generations of people are born, live and die during the journey, with only their distant descendants reaching the destination. Another idea is suspended animation or cryogenic freezing, though we don't have the technology yet. Interstellar travel is one of the greatest challenges humanity faces. The distances are so vast, the timescales so long, that reaching the stars requires not just technology, but patience, commitment, and hope. The speed of light limits how far we can go. Even if we could travel at the speed of light, which we can't, the universe is so large that most of it would still be out of reach. The Andromeda galaxy is 2.5 million light-years away. Traveling at light speed, it would take 2.5 million years to get there. By the time you arrived, Earth would be unrecognizably different if it still existed. The expansion of the universe makes things worse. Distant galaxies are moving away faster than light, meaning we can never reach them, no matter how fast we travel. The universe is vast, and we're trapped in a small corner of it, limited by the speed of light and the expansion of space. Some scientists dream of warp drives. In science fiction, warp drives allow faster-than-light travel by bending space around a spacecraft. The ship doesn't move through space. Space moves around it. In theory, this doesn't violate relativity, because the ship itself isn't moving faster than light. It's a clever idea, but it requires exotic matter with negative energy, which may not exist. Even if it does, the energy requirements would be astronomical. Warp drives remain firmly in the realm of speculation, but they're not ruled out by the laws of physics. It's possible that a sufficiently advanced civilization could manipulate space-time in ways we can't yet imagine. For now, it's a dream, but a tantalizing one. Wormholes might allow shortcuts through space. A wormhole is a hypothetical tunnel through space-time, connecting two distant points. If wormholes exist, you could enter one end and emerge at the other, potentially light-years away, without traveling the distance in between. It's like a shortcut, a bridge across the universe. Einstein's equations allow for wormholes, but they're unstable and would collapse unless held open by exotic matter. We've never found a wormhole, and we don't know if they can exist in nature. But if they do, they could revolutionize travel, allowing us to explore the universe in ways we can't currently imagine. Wormholes are theoretical, speculative, and thrilling, a possibility that hints at a future beyond our current limitations. The universe might be one of many in a multiverse. Some theories suggest that our universe is just one of many, perhaps infinitely many, in a vast multiverse. These other universes could have different physical laws, different constants, even different numbers of dimensions. They might be completely separate from ours, impossible to reach or observe. The idea comes from theories like eternal inflation, which suggests that new universes are constantly budding off from existing ones. If the multiverse is real, it raises profound questions. Why is our universe the way it is? Are we special, or just one random universe among countless others? The multiverse is speculative, but it's taken seriously by some physicists. The anthropic principle asks why the universe is hospitable to life. The physical constants of the universe, like the strength of gravity or the charge of the electron, seem finely tuned for life. If they were even slightly different, stars wouldn't form, atoms wouldn't be stable, and life as we know it couldn't exist. This fine-tuning is puzzling. Is it just luck? Did someone or something set the constants deliberately? Or are we in a multiverse, where every possible set of constants exists, and we just happen to be in one of the universes where life is possible. The anthropic principle suggests that we observe the universe to be this way, because if it weren't, we wouldn't be here to observe it. It's a tautology, but it's also a profound statement about the relationship between the universe and the life within it. The universe is governed by physical laws. Everything that happens in the universe, from the orbit of planets to the decay of particles, follows physical laws. These laws are mathematical, consistent, and universal. They're the same everywhere, in every galaxy, at every time. Gravity pulls, entropy increases, energy is conserved. These laws are discovered through observation and experiment, refined over time as our understanding deepens. Why the universe follows these particular laws and not others is a mystery. But the fact that it does allows us to understand it, to predict the future, and to look back at the past. The universe is not random. It's ordered, lawful, knowable. Science is our best tool for understanding the universe. Through observation, experimentation, and reason, science has revealed the structure of atoms, the age of the universe, and the forces that govern stars. It's not perfect. Science is always provisional, always open to revision when new evidence appears. But it works. It has taken us to the moon, cured diseases, and connected the world. Science is a process, a way of asking questions and seeking answers. It's how we've come to understand that the Earth orbits the Sun, that galaxies are moving apart, that we're made of stardust. Science is humanity's collective effort to make sense of the cosmos, and it's the best method we've found. Thank you for spending this time here, drifting through the cosmos with me. We've traveled from the nearest planets to the farthest galaxies, from the smallest particles to the largest structures, listening to the quiet hum of space, time, and light. And somewhere in all of it, in the glow of distant stars, in the silence of the void, in the gentle expansion of space itself, there was you, breathing slowly, thoughts softening, maybe even already asleep. This universe is full of motion and mystery, but also peace. It holds fire and ice, light and dark, and the quiet spaces in between. And the fact that we can know it, piece by piece, in rest and in wonder, is something truly beautiful. So, wherever you are now, whether you're fully awake or drifting beyond the edge of thought, may your dreams tonight be gentle. May your body rest like starlight on water. And may you carry with you, even faintly, the memory of a universe that glows, expands, and dreams, not just above you, but within you. If you happen to still be awake, you can go ahead and watch the next chapter now. And if you'd like to drift off to more stories like this, softly told, filled with wonder, consider subscribing. There's always more to explore, one sleepy soul at a time. Good night.